two questions. What's the volume of that? What's its surface area? Those are the two questions. We're going to do them one at a time. All right, so first let's find the volume. All right, if we're going to find the volume, then we're going to take this shape, right? We're going to wrap it around the x-axis. So here's our axis of rotation, right? I'm going to use vertical rectangles, right? And so I'm going to be using the method of washers for this. Now I'm assuming that y'all are somewhat comfortable with this at this point. So what is the formula for washers? You have it here. It's on this handout. Whoa, shit. There it is, very first one, right there. Right, we're wrapping a region around here, right? Can you all tell me, well, let's see, it'll be pi, right? Integral from where to where? 1 to infinity, right? 1 to, oh, it's an improper integral. We've studied these. We're going to have a limit at some point. All right? So we go 1 to infinity, pi. Okay, outer radius squared. Outer radius is the distance from the axis of rotation to the outer edge. What is that? What's that distance right there? Just 1 over x, right? And then what's the inner radius? It's always what? 0, right? The bottom edge is always on the axis of rotation. So this should just be 1 over x squared. Do I have to put minus? I'll put it minus 0 squared dx. There it is. That's what we have to do. All right, this becomes pi. Let's do it this way. Limit t goes to infinity of pi times the integral from 1 to t of 1 over x squared dx. Y'all remember how to do this? We got improper integral, replace the infinity with t, take the limit. Okay, this is 1 over x squared. That should be pretty okay, right? Taking the antiderivative of that. Just remember, this is the same as x to the negative 2. Then use your power rule. Here we go. Limit t goes to infinity. All right, pi. Okay, the antiderivative of that is negative 1 x to the negative 1, or negative 1 over x, right? Do y'all agree that's the antiderivative of that? But now we need to evaluate this from 1 to t. Questions? Okay, this equals, all right, limit t goes to infinity. All right, now we're going to plug in the two things, right? All right, when I plug in t for x first, I get pi times negative 1 over t. Ugh, I gotta sneeze. When I plug in 1 for x, I get pi times negative 1 over 1. And now, let t go to infinity. What happens here when t goes to infinity? It goes to 0, right? Fixed number over something gets huge, that goes away. This thing all basically vanishes out to 0. And then I have minus, and then this in here becomes negative pi. And negative pi is pi. That's weird. It's finite, it converges. This improper integral converges, which means this Gabriel's horn has a finite volume, right? Has a finite volume. We haven't reached the paradox. We're halfway. You all ready to continue? Okay. Now let's do surface area. So to do surface area, I've got to do area is 2 pi, integral from 1 to infinity. Okay, what now? 1 over x, that's the function, times the square root of 1 plus, okay, I need the derivative of the function squared right here, don't I? Okay, I haven't done that. I need to go over here and do that real quick. Yeah, no, I'll erase it. Y'all have any questions on what I'm doing here? I'm setting up the area formula. I need to know if my original function was 1 over x, I need to know the derivative of that, which is negative 1 over x squared, right? That's the derivative. And then I need to take that and square it, which is 1 over x to the 4th. 1 over x to the 4th. Got it? And guess what? That integral is not doable. We can't do this. But I'm going to go back to a property of integrals and use this property. So does anyone have a question up to this point? We've got the integral set up, we just are not sure how to do this yet. So I want to go back and ask you a question, or see if you remember this. I told you when we were talking about integrals, if you had some function that was always bigger than or equal to another function, so when you graph this, it's above or at least equal to this function, right? Do you all remember me saying then the integral of that function should be greater than or equal to the integral of this function, which basically just meant that the area under that curve should be bigger than the area under that curve. Do y'all buy that geometrically? Yes? Okay, so this one's above. Okay. If you believe that, then what I'd like for you to do is just kind of completely forget how we got here, okay? Forget how we got to this point. I just want you to look at this function right here. And this right here, I want you to look at it as being the f of x over here. It's some function that I'm doing an integral of, right? What I want you to kind of wrap your head around is that this function right here is greater than or equal to this other function, g of x, and I'm going to tell you what the g of x is. Just 1 over x. You have to now convince yourself that what's in red will always be bigger than what's in green. Do you buy it? Do you believe that this right here, this quantity, whatever it is always bigger than 1 over x? Well, they're both the same here, right? They're both 1 over x, which means I'm trying to convince you that this piece right here is bigger than what? 1. So imagine there's a 1 next to this, right? Do you all agree that this quantity has to be bigger than 1? Yeah. Why? What's 1 over any number to the 4th power? Positive, right? Positive. What's 1 plus a positive number? Positive, bigger than 1 though, right? Square root of a number that's bigger than 1 is still bigger than 1. This quantity right here is definitely bigger than 1. So 1 over x times a number bigger than 1 should be bigger than 1 over x, right? Which means this. Which means that this integral right here, this integral should be greater than or equal to the same integral, 2 pi integral 1 to infinity of just 1 over x dx. See, if I replace, it's this right here, right? This integral, this was our red one, our red integral, has to be bigger than the green integral because the f was bigger than the g. So the area under this has to be bigger than the area under that. The area under this is bigger than the area under that. Y'all buy that? Do y'all remember this example? This is one of the first improper integral examples I did in class. It's in your notes. What did we get for that answer? We got infinity. We got infinity. So we're trying to find the surface area of something, right? The integral that we set up, we know that this answer has to be bigger than or equal to whatever this is. But this is infinite, which means this must be infinite as well. The only way you can be bigger than infinity is if you're infinity. So that forces this to be infinite. So this is infinite, which means your area is infinite. Thus the paradox. Why is that a paradox? Your volume is finite, which means if I could fill it with paint, right? Pour paint into it, it would hold exactly pi units of paint. That's finite volume. However, this says I can't what? I can't paint the surface. The area of the surface is infinite. It's a paradox. We're not going to get into like debating it and stuff like that. You can go Google it and you can find more information about it. It has to do with the fact that when we talk about areas, right? Like if I want to go paint this wall, right? If I want to paint this wall, let's say I want to paint the whole room, right? I go to Lowe's or Home Depot or somewhere, right? And I go get a gallon of paint. And on the gallon of paint, on the back in the real small little writing, it'll say coverage, right? It'll tell you how much that gallon will cover. It'll say it on the can. And it normally says something like 300 to 400 square feet is what it normally says on a gallon of paint, standard paint. 300 to 400 square feet. So it's saying that when you paint this, right, you take the area of that and that's how much it should cover. In reality, is paint on a wall two-dimensional? In reality? No, it's got thickness, right? So when you talk about this can has a volume, right? When you put it on the wall, that paint has thickness. So you're putting a volume onto the wall, not an area. Areas in mathematical terms, areas have no thickness. So we get confused when we talk about areas in the real world because technically they're volumes, right? Like when you talk about covering a surface. All right, we'll leave it alone. Chapter 7's done. Promise this time. Are you all ready? We have 20 minutes. I feel like we need to have like a pep talk or something first. So it's November, right? We're coming up on Thanksgiving, right? Everybody, after Thanksgiving, everyone's already checked out. You come back, and it's just, you just want it to be over, right? But we are now starting the hardest chapter of the class. I'm only speaking from experience, all right? I'm not, who knows, maybe you'll do really well with it. You never know. I can never predict how people are going to go with this. What I can promise you is it's a lot of material, okay? So we need to somehow regroup, get that eager day one sort of motivation back, right, to take this on. All right, so I have notes, right? I have notes for this. But yeah, let's just get into this. I'm going to show you, I initially wanted to like show you the finish line first. Like why, right? Why are we going to do all this? I'll do that next class, all right? For now, let's just get right into chapter 8, all right? And the first section in chapter 8 is called Sequences and Series. Here's the first section, Sequences. And as you see here, I have 24 notes for just this section, right? Now, there are two different words in chapter 8, sequences and series. They are not the same thing. So make sure when you're listening to me, you're distinguishing between the two. 8.1, sequences. 8.2, series, and then from that point on, we just do series. But sequences is the foundation of everything. So that's why I like to spend as much time as necessary in here. I'm going to put this definition up here. Remember, don't sit here and try and copy all this down. There's no way you can copy all these notes and keep up, right? So just know that they're available to you. All right, a sequence. It's a very simple definition. A sequence is a function. We've been dealing with functions, right? A sequence is a function with one restriction. See, the functions we've been dealing with in this class, we've called them f, right? Like function. And what they've done is they've taken a real number in and they've spit a real number out. So we say that it goes, a number goes in, number comes out. Real number goes in, real number comes out. So for example, if I gave you a function like f of x equals x squared, right? That's an example of a function. If I did a little t-table, go back to like grade school, elementary, high school, I don't know when it is. X, here's f of x. You can start plugging numbers into this, right? You can plug in 0, 0 squared is 0. You can plug in 1, 1 squared is 1. You can plug in 2, 2 squared is 4. Those are nice numbers we're plugging in. But you can plug any number in, right? Any number. You could plug in, 1/2 if you wanted to. 1/2 squared is 1/4, right? You could plug in 1/3. 1/3 squared is 1/9. There's no restriction on what you can plug in for x. It can be any real number, so long as this is defined, right? Of course, you had like division by 0 or something, like 1/x. You can't plug in certain numbers. But other than the domain restrictions, any number can go in. Decimals, fractions. You could plug root 2 into this, right? Square root of 2 go in here, square it. A sequence is a function where what we've done is we have restricted this to no longer be any number, but only natural numbers. We use a double struck n. They do it different ways. I do it that way. Computers do the double struck across like that. I always do it like this. So everyone's familiar with this notation, right? Real numbers, all real numbers. This is the natural numbers. What are the natural numbers? The numbers that human beings naturally started with. We started with 1, then 2, then 3, then 4. And then later came 0. 0 came, it was actually like this huge, whoa. We realized the idea of nothing. And then, whatever. So the natural numbers, 1, 2, 3, 4, right? So if we take a function and we restrict that function from the natural numbers into the real numbers, you're now looking at a sequence. Oops. You're now looking at a sequence. And that's it. That's it. That is the definition of a sequence, right? Now, what we do, though, is we change the notation because we don't want to be using f for function and then have to somehow tell you, hey, restrict the domain to the natural numbers. So what we do is we change the notation, and here's what we've got. So instead of using f of x, we write this. We write a sub n. Look at that as being like, look at it as like an evolution. To get to that, what we did is we said, okay, we have a function of x, right? But we're going to restrict the domain where this can be any natural number. Let's call it n. So now, does that kind of imply to you that instead of using anything, you can only use natural numbers? And then we say, well, wait a minute, you know what? Let's not even use the f anymore. Let's call it a of n. So it's a function This time the name of the function is a. Look, I didn't choose that letter. That's what mathematicians have used. Now n's getting plugged into this function called a instead of n getting plugged into the function called f. And then going even further, we said, okay, forget that. Let's just use that n in a subscript. So this is the input, right? And this is the function. This is the name of the function. That's it. Now, the other thing is, on a regular function, in order to know the output, like we need to know where the input came from. Do you all agree that our inputs, we all know what they are, right? Like what's the first input we could possibly have? Natural numbers. So 1, right? Then 2, then 3, then 4, then 5, then 6, right? So the only thing you can ever, if the only thing you can ever plug in are the actual natural numbers, then instead, what we can do is we can look at a sequence as being a list, set of braces for, for the list, and all we're going to do is list the outputs. That's it. We're just going to list the outputs because we know what the inputs are. So this will be the value of a at 1, the value of a at 2, the value of a at 3, and so on and so forth. We'll put 3 dots and then another brace to imply that that goes on forever. Now look, the easiest way to see a sequence is for me to just give you an example, right? Let me just get you an example right now. Example, I'm going to define, let's let a sub n equal 3n plus 1. There you go. I've defined a sequence for you. If we were not talking about sequences, this would be the function, right? This would be the function I'm talking about over there. So it's just a different notation, right? The difference between these two is that here I can plug in any number. Here I can only plug in 1, 2, 3, 4, 5, 6, right? That's it. So what I can do is I can just start listing the outputs of this sequence. So this is going to be, all right, what do we start with? 1. Plug 1 in, you get 4. Okay, now plug in 2. 7. 10. 13, dot, dot, dot. It keeps going, right? What we have to see is that this is what you get when you plug 1 in. This is what you get when you plug in 2. This is what you get when you plug in 3. This is what you get when you plug in 4, and so on and so forth, right? Questions? So far, everything's clear? All right. I gave you an example here in the notes where I gave you the example is a sub n. Oh, that's the way we say that. A sub n, subscript n, a sub n is equal to n squared. That would generate this sequence 1, 4, 9, 16, dot, dot, dot. Now, some sequences are finite. Some of them are infinite. I need to make that a little bigger. There we go. So if your sequence, why is it doing that? If your sequence is infinite, then all you write down is the sequence a sub n. You can also, next to it, put it in a set of braces. You could put n equals 1 to infinity, and that lets everyone know it goes forever. Or you just write them out and put dot, dot, dot. That lets everyone know this sequence goes forever. But if you want to stop the sequence, right? Like, let's say we only want to go, start at 1 and end at maybe 7, like a sub 7, then I need to somehow let you know that. So what I do is I could say a sub n in a set of braces, and then n equals 1 is where I start, and that's where I stop. So you go 1, 2, 3, and you stop at k. You all see that? Let's see if you see it. Let's use this same example right here, right? Same example. Watch the way I write this, okay? So that just means start at 2 and end at 5. Okay, so this should generate this sequence of numbers. 2 goes in first, you get 7, then 10, then 13, then 16. That's it, right? As a finite sequence, finite number of terms. So I plugged in 2, then 3, then 4, then 5. I stopped. Finite sequence, infinite sequence. We are going to study in this class almost exclusively, what do you think, finite or infinite? Infinite, all right? We are interested in infinite sequences, not finite sequences. Question?
So, where it says from n equals 2 to 5, is that like...
It's like an integral. It's like the limits of integration, but not quite. I mean, it's what we call indexing. We're indexing the sequence, starting point, starting index, stopping. The difference is that on an integral, it's 2 to 5 and everything in between, right? Here, this is 2 to 5, but only natural numbers, 2, 3, 4, 5. But it's the same sort of convention of having a lower limit and an upper limit.
And this is how it's written, right?
Yeah. I mean, there's a lot of different ways to write a sequence, but if you wanted to have that sequence starting at 2 and ending at 5, that's the way you would write it. If you just wanted this sequence forever, like to start at 1 and go forever, then just write it like that. You do not have to be explicit about it being infinite.
Why is it that on the upper limit, it's just the number and not the n equals?
You could put n equals, but it's kind of understood. It's understood that if n starts at 2, then it's going to end at 5. Kind of that. See how they have it there? It says n equals 1 to k. You just put k. You don't have to put n equals k. Wouldn't be wrong. You could do it. Wouldn't be wrong. All right. How we doing? Yeah. That clock's wrong. We have 7 minutes?
It's been dead all semester.
Yeah, has it been all semester?
Yeah.
It was actually dead last semester.
Really? Okay, it's been that long. Okay, well, you know what? What does it use? Let's see. AAA? Huh? AAA, I'll bring one. Okay. We only have a few minutes. So what we need to do, the next part, and this is where things start to get foggy, is that this is not the hard part. The hard part is not me giving you the function, asking you to find the sequence numbers, right? The challenge is the other way around. If I give you the list of numbers and ask you to figure out the sequence, that's harder to do. So let's start with, in the last 5 minutes, let's see if you can come up with the formula for this, all right? And we're going to start out easy, and we're going to get harder and harder. So I want you to raise your hand. Don't just blurt out an answer, all right? Here's the sequence. Now, when it comes to sequences, you have to give enough numbers where reasonable people can find the pattern, right? Like if I just gave you one number, that wouldn't be enough, right? Okay. Now keep in mind, when you volunteer your answer, you're out, okay? You won't be able to answer these questions until we cycle through everyone. Okay, do you want to keep with it? Do you have a formula for this? A sub n is what? 2n. There we go, 2n. Those are your even numbers, right? Even numbers. If I plug in 1, we get 2. Plug in 2, we get 4. So on and so forth, right? Put a little note next to that. This is your even numbers. All right, how about this one? So I need a volunteer. If I don't have volunteers, I'm just going to call on people. All right, what do you got?
2n plus 4.
2n plus 4. What do y'all think? 2n plus 4. Do you have a question?
Oh, no.
You have another Another idea for this one? What was your other idea?
It would be 2n, but n would equal 3.
Okay, so you're suggesting we could go 2n, but n starting where? At 3. That would be correct notation-wise, right? This would be the same thing, right? Because you start at 3, you'd get what? 6, then. And since there's, oh, we should put infinity up here if we're going to follow that. That would be the same, right? So although this is correct, right? Although this is correct, it doesn't help us later to use this notation. This is what we want to be able to see, all right? Because we're going to be combining a bunch of different sequences together, and we can't have some of them starting at 3 and maybe another sequence starts at 5 and the other one starts at 7. We want them all to start at 1. So do y'all see that these two are almost the same, right? 2, 4, 6, 8. They go up by 2, right? They keep going up by 2 each time. This one starts at 2, this one starts at 6. This one's 4, this one's 8, this one's 6, this one's 10. So what's the spacing between these two numbers? We're just adding 4, right? So it's just, all we're doing is we're taking this formula and adding 4 to each of the numbers. And we get this, right? So good. All right, how about this one? How much are they going up by to get from one to the next?
2.
I'm adding 2 each time, right? That's what all these are doing, right? 2, 2, 2, 2, 2, 2, 2. It's just where do you start from, right? Did you have an answer? 2n minus 6. This, take away 6. That, take away 6. That, take away 6. That, take away 6, right? That works. One more. One more. How about this one? One, 3, 5, 7, 9. 5, 7, 9. I don't think you need the 9, but I'll put 9 in here. Okay, who wants that one? Go ahead. 2n minus 1. And these are special, aren't they? These are what? Odds. Now, how much are they going up by each time? 2, 2, 2, 2. That's why we have a 2n. But the minus 1 just moves it, right? So it's like we took every even number and subtracted 1, and we got all the odds, right? What would this be? I said one more, I lied. What would this be? 3, 5, 7, 9.